All right. So, do we have Polina? All right. Next up, we have Polina Binder, a data scientist at Cambridge Mobile Telematics, focusing on modeling distracted driving and on computer vision. She obtained her bachelor's in math and computer science from the University of Toronto and master's in computer science from MIT.
Hello. So I'm Polina, and I'm a data scientist at Cambridge Mobile Telematics. Our company's mission is to make roads safer by making better drivers. And we do this by determining what sort of driving behaviors are dangerous, and then helping drivers improve their driving behavior and providing other services that make driving safer. So first, let's discuss the magnitude of the problem of dangerous driving around the world. Around the world, there are 50 million road injuries every year and 1.25 million deaths. And additionally, this affects countries all around the world, but to varying degrees. Just in the United States, between 2014 and 2016, there has been a 14% increase in road fatalities, and this trend is only continuing to this year. A big cause of this increase is distracted driving, so when people are looking at their smartphones and their eyes are off the road. So we found that 36% of the drives in the US have a significant amount of distraction. So if people not actually looking at the road, but looking at their phones. So our mission, as I mentioned, is to make roads safer by making drivers better. And we do this with our DriveWell platform. So in this platform, we use sensors that are on a smartphone and also on an external device for some of our customers. And we process the data from these sensors using various machine learning and signal processing techniques to identify when people are driving dangerously. And we use behavioral science to try to modify people's driving behavior. So our main clients are insurance companies, and we provide actionable insights for them and measure who is driving dangerously for them. And we find that our program actually significantly reduces various dangerous driving behaviors. So our company started as a startup at MIT in 2010, and now we have over 30 insurers and hundreds of fleets around the world. We're in over 20 countries and growing, and we recently got $500 million from SoftBank. And this map shows where we have various users around the world. So we have billions of miles of driving data from millions of users, and so we can leverage all of this various data to understand what sort of driving behaviors are dangerous and where dangerous is most likely to lead to a crash. So how do we do this? So the main types of dangerous driving events that we're trying to detect are braking events, acceleration events, and phone distraction events. So when someone is playing with their phone and not looking at the road. We also monitor when people are speeding. But we don't only detect these events. We place them in the context of the time of day and the road type to understand how truly dangerous they are. So one of the more interesting questions that we try to understand is when humans are actually distracted. We do not use a rear-facing camera into the car, so we measure distraction based on sensors that are in the smartphone. So basically we have a large amount, and additionally we have a large amount of unlabeled data in this problem because we can't really ask people to drive at high speeds and play with their phones because that's just incredibly dangerous. Of course, in my darker moments, I would love that data. So additionally, we've partnered with PBS to make a documentary about distracted driving, and these are some things that people did in their car when they knew that they were being watched. So they'll do stuff like this, move their phones around, and just like even if you're distracted for a few seconds, it's a pretty major problem. Yes, stuff like this. Yeah, that one is a bit harder to detect because they don't have the phone in their hands, but yeah. Then other weird things that we'd like to be able to somehow capture. It's pretty amusing. Yeah, and this is all people that they know that they're being watched. So imagine what they're doing when they're not being watched. So in terms of, okay, so there's this thing, it's kind of funny, but we'd like for people not to do it. So first we need to measure the degree of the problem. So we do this using various sensors that are in the phone, primarily the accelerometer, which captures how the acceleration patterns in the phone, and a gyroscope, which captures rapid changes in the angle of the phone. So when it's being moved around, you see that the gyroscope changes. We know the screen state, so if it's on or off, we can capture whether someone is calling and whether that's hands-free or not hands-free. We can tell when someone is texting or tapping on their phone. And we put all of this in context of the vehicle motion state to understand how dangerous it is, and also to separate some of these signals from the car's motion. So as I mentioned, we find that 36% of trips in the US have a lot of distraction. And we also see that about a third of the distraction happens at speeds of over 50 miles per hour. So this is an incredibly dangerous phenomenon, because you can imagine that you might need to react incredibly quickly there. So another truly disturbing thing with distraction is this concept of a distraction hangover. So this has been studied in lab settings where if people interact with their phones, they're slightly impaired on cognitive tasks for approximately 30 seconds afterwards. And we found that this pattern holds for driving also. So we can examine harsh braking rates after someone has been interacting with their phone and compare those to harsh braking rates when they haven't been interacting with their phone. And we find that after people have interacted with their phones or been on a phone call, they're more likely to brake harshly in the next 30 seconds than if they hadn't been on a phone call or interacting with their phone previously. And this holds even if you normalize by speed or by all sorts of various criterion. So this makes a great argument for trying to understand phone distraction and discouraging people from doing it. So now let's dig into the sort of data that we actually obtain when we're looking at someone's drive. So here we have someone who's driving on Memorial Drive, and you might recognize this road segment. It's near Harvard. And in green, we have the route that the driver took. Then in blue are the areas where we detect that the driver was distracted. And if you've ever driven there, those blue areas are right before intersections, and they're places where people are more likely to be stopped in traffic and actually interacting with their phones. So we can determine for how long those distraction events occurred. So for example, for this drive, it's for a total of 30 seconds. We can distinguish what type of distraction it was, whether someone was moving their phone around or in certain areas they were tapping on the phone. So we can paint this sort of nuanced picture for exactly in what ways someone was driving dangerously. And moreover, we can assign a numerical value to how dangerous each of these two distraction events was. So what we do is we assign a given number of risk points to each distraction event, which captures how dangerous they were. So how likely this type of distraction event was to lead to a crash. And we do this by placing in context of the speed, of the road type, and by the time of day that the event occurred at. So that's an overview of the distraction on the level of the trip. But if we actually look at the data that we're using, so that's shown here. So on the top graph, we have the accelerometer data. So the acceleration of the phone in each of the 3 dimensions. The second graph has the gyroscope data, which captures changes in the angle. And the bottom graph has the GPS speed and the GPS heading, so which direction the car is in. So one thing to note here is that during this time segment, the heading of the car is unchanged. So the changes in the accelerometer, and the speed is fairly stable. So the changes in the accelerometer and the changes in the speed are likely due to phone motion that is independent of the vehicle. So probably due to someone moving the phone around. So at the top in the box, we have this repeated kind of accelerometer pattern. And we've trained a classifier that identifies that as a tapping event. So someone is like picking up their phone, sending a short text message. We can say that this is occurring for a certain amount of time at a given speed, so it gets, say, 10 risk points. On the second graph, I've drawn a box around where there are big changes in the gyroscope. So these would occur from someone picking up the phone and moving it around. So we know that this happened for 7 seconds, the speed, so we assign some risk points to it. And then for a given user, we can get a certain number of risk points for the trip. And then we can see how they've been driving over the course of weeks or months and how well they drive on average. So we can assign each user a score that tells us how dangerous of a driver they are. And our goal for these scores is that they would be predictive of drivers who are likelier to get into crashes. So in the actuarial world, what is used for this are lift charts. So I'll walk through this because I haven't really seen them used anywhere else so much. So let's look at the chart on the left. So on the x-axis, we have users who are grouped into deciles based on how much distraction they exhibit. So users over some time period. So users in the first decile exhibit the least distraction, and users in the last decile exhibit the most distraction. And on the y-axis, we have the relative crash risk for these users to get into an accident. But it's interesting that it's in the time period, not when we were measuring the distraction, but in a time period shortly after. So we're actually answering the prediction question. If you've, say, been driving this way for 3 months, how likely are you to get into a crash the next 3 months? So let's say that our distraction score was completely not predictive of people getting into crashes. Then users in the first decile would be just as likely as users in the last decile to get into a crash, and this blue line would be horizontal. But we don't see this. What we see instead is that users in the last decile are 13 times more likely to get into a crash as users in the first decile. So this is an excellent argument for putting the phones away. Then if we combine all of the risk scores that we have, so this is where we look at a user's phone distraction, their braking, their speeding, all this data put together, we find that the top decile of users is 22 times less likely to get into the crash than the worst users. So this way we can model the sorts of dangerous driving behaviors that people do. And as you can see, they're predictive of whether or not you will get into a crash in the future. So this is great. For insurance companies, this is amazing information. You can reasonably distinguish users, not just based on, say, gender or marital status, but based on how they're actually driving. But we want to go beyond that. We want to actually make driving safer for everyone. So how do we improve the driving behavior? So a part of our platform is an app, and there are various rewards in that app. We conduct contests where we partner with cities to determine that and give cash prizes for the safest drivers. So one such contest we recently conducted was the Boston Safest Driver competition in the city of Boston. And there the city also used insights from, anonymized insights from the data that we produced to try to determine some city planning choices. For example, they moved a bus stop a few feet down the street where it would be safer for people to get on the bus based on data that we'd provided. Additionally, we also have leaderboards and various other social features in the app. So in terms of how well this works, so this graph, let's go through it. So on the x-axis, we have the days of the program for our 50% most engaged users. On the y-axis, we have the frequency of braking and phone use compared to the first day for these users. So let's say that the users in our program just wouldn't have improved, just wasn't working. Then the users would just return to the blue line. So after very many days of the program, they would have the same harsh braking rates and the same phone distraction rates as they did during the first days of the program. But this isn't what we see. We see that the harsh braking rates pretty rapidly decline at around 15–20%, and then they continue declining throughout the program, more or less. And this trend continues for about a year. So we're actually discouraging this behavior. And with phone usage, we see an even harsher decrease, that people rapidly stop using their phones, almost to 50% for more engaged users, and then this trend continues throughout almost a year in our program. So we're actually affecting long-term change in these dangerous behaviors. So I've discussed how at Cambridge Mobile Telematics, we leverage a large amount of data we have to identify dangerous driving behaviors, assess users based on these behaviors, and finally to improve the user's behavior. But we have a lot more fascinating machine learning and data science problems. One of them is trip mode classification. So in this problem, we know that someone is moving, but what if they're the passenger in the car? We need to be able to distinguish that and because then it's fine for them to be playing with their phone, or then the driving isn't their fault. We need to be able to tell if maybe they're biking or walking or on a bus. So that's another problem that we deal with. Another interesting problem that we encounter is the problem of analyzing crashes after they occur. So here we want to be able to reconstruct a crash based on the sensor data that we have, and want to say, maybe be able to assign who's at fault or which part of the vehicle was affected during the crash. Another interesting problem that we deal with is the problem of crash detection. So in this setting, we have a small external device that measures acceleration that should ideally be attached to the car. So this might sound like a fairly simple problem. Well, someone got into a crash, there's a giant accelerometer pattern, but it's not always that simple. There are a lot of cases that look like a crash, like a door slamming, or the phone was just thrown around in the car, or the small external device wasn't attached. Human silliness knows no bounds here. So this is a very fascinating machine learning problem. And this has a very important social implication too, that if you detect the crashes, you can automatically notify the insurance companies or emergency services, because in very many cases, people just can't notify the services themselves. So next I'll show a video that our clients in South Africa made about this product.
It hit me so hard I was forced under a bus, and there was smoke everywhere. I tried to get out, but both doors were jammed. I jumped out the back door, and the first thing I did was phone my mom. Whilst I was talking to her, emergency services arrived. The force of my accident alerted Discovery Insure, and they immediately sent help. A paramedic rushed up to me, grabbed my arm just as I passed out, and when I came to, I was safely in the ambulance.
So this is just another way that we use all of the driving data that we have gathered to make driving safer for everyone. Thank you very much. Yes.
Thanks for a really interesting presentation. I'm curious about the lift charts that you showed and the relative crash risk, I think.
Yes.
It's called. Are those computed from like industry-wide standards based on demographics or something, or are those computed from like actual accidents in your training population?
So these are all from actual accidents in our training population. I don't think that there are enough that they're like really good industry-wide standards for this, or just like good data sets, because I don't think other companies have this amount of telematics data.
That's really cool.
Okay, hi. Sure. So question on if you're using a data for an application, when I think of driving in Boston, I mean, I'm from the Midwest and it seems a little safer to drive out there. Do you use any of the data to look at maybe potentially dangerous intersections and traffic patterns that might be causing accidents?
Yes, we do that quite a bit, actually. So as I mentioned, for the city of Boston, we found dangerous intersections, and that data was used to even move certain bus stops around and might be otherwise used for city planning. And for a lot of the safest driver competitions, we also generate charts of where dangerous intersections or dangerous road segments are.
Thanks for the presentation. Hello. So I once used the progressive insurance, and they provided me a built-in device called a snapshot by supervising my vehicle.
Mm-hmm.
So how do you make sure the accuracy of your data? So I mean, like the road situations. You mean the app to monitor our vehicle, right?
Mm-hmm. So in terms of ensuring accuracy, we have a QA team that ensures that the app is behaving as we expect it to, and we all also like check on it also, and we test all of our code carefully and that sort of stuff. And so, okay, let's see. What other? Were there any like specific things about it that were of particular concern? Because there are a few extensions that this could go on, but I want to address your question.
Yeah.
Okay.
Thank you.
So you had mentioned that you guys got some investment from SoftBank recently.
Yes.
So I'm really curious because they have all of these app-based gig economy drivers, like with food delivery and DoorDash, and I forget which of the ride-hailing services they've invested into lately. So have you guys been also integrating with some of those? Because I feel like that's a lot of people on roads. It's a lot of vehicles on roads.
I'm not entirely sure what like those business plans are for the company.
I was wondering whether the driving data is actually replacing the demographics data or adding to it, and if it is replacing what it should be, did you compare the prediction accuracy?
So ideally it would be replacing it, and from what I know at the early stages of the company there were comparisons and this does a better job.
Yeah, can I ask a more specific question? So so you mentioned you have a classifier for the tapping.
Mm-hmm.
Can you describe in a little in more details, like what important features you use for the classifier?
Let's take that one offline actually, like the specific implementation of it.
I'm sorry?
Let's discuss that afterwards, the specific implementation of it.
So I have a question about the long-term behavior change graph you showed. So what you showed 50% most engaged users. What's their retention rate? I'm just wondering whether the curve you showed has some survivorship bias because it's like a year after.
So we have similar stats for all of our users, and then so here we had that the phone distraction rate was okay. Let's go back to this one. No, it was sorry here. So like that the phone distraction was reduced to say 45% or so. For if it were for all of our users, then it would be like around 60% or something. So I'm not sure about the specific retention rates because those often end up varying so much by the insurance company and their specific policies and how they're using the products that we provide.
Hi, I was curious about how much your binning into the different deciles for the risk correlates with the frequency of driving. So meaning, is someone that drives more frequently being more often distracted? And then kind of as a follow-up questions, are you worried that with your algorithm you might penalize people who just like drive a lot and then basically they're more likely to be distracted?
So that is a valid concern, but these lift charts were normalized by driving distance, and our scores are all normalized by driving distance.
Yeah, it seems like if something like this, this level of analytics becomes really widespread, there's going to be real incentive for gaming. You know, whatever, installing it in your burner phone is the easiest thing I can think of, and then putting that in the back or what have you. Is that something that the company is, or you're thinking about as a data analyst? Is that something the company is thinking about that you know of?
So there was actually a problem with Pokemon Go and GPS spoofing, which was similar, and there was work on that before. So yeah, it comes up a bit.